Hi, everyone. Thanks for joining us today. I'll give it a few minutes for everyone to be able to join us, but welcome to the Out of the Box and Beyond with Photogates webinar. I'll be introducing your presenter, Tom Smith, and Burl Walters is also in the background. He's going to be helping answer questions during the session today. Just to let everybody know, we are recording the session, so that will be available as a resource after today. And you'll also be getting a follow-up email that includes the recording. I'll be sharing a link in the chat in a moment to some resources in a shared folder, and you'll also get a certificate of attendance. So with that, we'd love to answer your questions during the session today. So if you could just put those in chat, that would be awesome. And we may have some time towards the end for you to unmute yourselves. But if you just put those in chat while we're in the session, that we can get those answered. And if we happen to not get to your question, we will follow up with you later. So with that, I will pass it on to Tom.
Great. Here, let me pop my talking head up here for a brief moment. Welcome, everybody. Tom Smith here from Vernier, part of the engineering education and physics education groups at Vernier. I'm going to start off today just by talking a little bit about the Photogates and the connection with graphical analysis, and then we'll go right into going through some setups of some basic data collection options with Photogates. The Photogates are kind of deceptive items because they are so simple, and yet there are so many different ways to use them that it bears a refresher periodically. And we're just going to scratch the surface today. There's plenty more options, especially regarding remote sensors connected to a Go Direct Photogate, that there may be an opportunity for kind of an advanced Photogate webinar in the future. But with that in mind, let me just jump into my notes here. A little anatomy up front. So we're going to take advantage of the Go Direct Photogate's features, primary feature being that it has two photo eyes. So has, again, has an infrared emitter kind of on the thick end of the Photogate over here. You can see those ports there, those two eyes, if you will. And on the opposite arm, the thinner arm, there are the receivers that are indicating whether or not the infrared light is being detected on that side or not. There is a laser port as well, and that's right here, labeled by letter E. And there are indicator lights for all three of these photo eyes. The indicator for the laser eye is right here, right up above the laser gate. And then the two photo eyes are indicated by a red LED in each of those locations for G and H. Of course, we see our power button here, which is an important feature. We are also going to look a little bit at ways to attach the Photogate to hardware. So we have a threaded nut on the thin end of the Photogate, thin arm of the Photogate. So you can attach a threaded quarter 20 threaded rod into that and mount it on a ring stand. We're also going to take a look at this ultra pulley attachment formation up here on the top of the Photogate. So that's kind of the big picture of what the Photogate looks like and what we're going to experience today. When you connect a Go Direct Photogate to graphical analysis and you click on sensor channels to expose all of the available channels, you'll see that there is quite a list. And I kind of have chunked this up into two groupings. On further reflection, I might have chunked it up into three groupings, and I'll talk a little bit about that. But we have here object velocity and object acceleration. Anything that has the word object involved with it is going to take advantage of both photo eyes on the Photogate. Further down below here, let me just talk about gate 1, gate 2, and laser gate. Those are just going to give you basically a timestamp when a Photogate is blocked, when an eye is blocked, and another one when it's unblocked. So it's looking for that infrared light, and if it sees the infrared light, it's good. Once it's blocked, it captures a timestamp, and once it's unblocked again, it captures another timestamp. The remaining Photogate options down here for our channels deal with remote gates having another Photogate connected to the Go Direct Photogate. And we may experience one or two of those today as well. Just to go into this in a little more detail, object channels, again, we're taking advantage of both of the photo eyes on the Photogate. And we know the distance between those two photo eyes. So it's really simple for us to get a velocity from an object rolling through a Photogate and capturing that information. It's an average velocity, but it's an average over a very short time span. So close to instantaneous velocity going through the Photogate. You can also, there's an object channel that just gives you acceleration data. So it's based on the velocity data, but if you have an object with multiple flags going through the Photogate, you can use that to calculate an acceleration. And this, again, this uses pulse timing, and I'm going to explain this in a fair bit of detail here in a moment, where it's blocking one Photogate and then taking the time until the next Photogate is blocked, or photo eye, if you will. The object-based channels default to time-based data collection. And we'll distinguish that as compared to Photogate-based timing a little bit later. Here is a screenshot of graphical analysis where I have actually 4 channels selected. I have object velocity, I have object acceleration, and I also have gate state 1 and gate state 2 selected. This is a little bit down in the weeds, so if you go have a cup of coffee for the next couple of minutes, I'll understand. But let me just walk through how the object velocity and object acceleration are calculated from this data. So again, it's using the blocked from the first gate to the blocked from the second gate. It has timestamps associated with those, and it uses the spacing that is known between the two photo eyes, 2 centimeters, and it calculates an average velocity. That velocity is assigned to the mid time between those two events, between the blocking of gate 1 and blocking of gate 2. Here we have the velocity associated with those two blocked events. Same thing happens. We don't do anything with the unblocked events. We just go to the next blocked event. We say, here's gate 1 blocked and gate 2 blocked, and we calculate an average velocity and assign it to the mid time of between those two gates. So now we're just going to continue on up the road here. Here's the next 2 blocked events. Here's the average velocity associated with those, and so on. So that's how we're going to generate our velocity data. And from the velocity data, we're going to calculate an acceleration. And we're just doing that by taking that final velocity, if you will, that second velocity and the first velocity, and getting a change in velocity and applying that change in time from those two events to determine an acceleration. and that acceleration is assigned to the mid time between those velocities. So again, just using this, and it's important to remember that these are approximate velocities assigned to midpoints, but that's going to, those two velocities are going to allow us to calculate an acceleration. And then the next two velocities, so this velocity and this velocity, are going to be used to calculate the acceleration and assign to the midpoint between those two velocities, and so forth. Okay, enough in the weeds on that. We won't torture you anymore with that type of detail, but it's useful to know when you're looking at where this data come from. So that was talking about the object velocity and object acceleration channels. The other channels typically have more special applications. Either you just want to know timestamps and gate states for some of your advanced physics applications, or you're working with remote photogates. You're interested in determining the period of a pendulum, you taking advantage of the laser gate, or looking into rotational dynamics. These are some of the things we're going to look at today. It provides you gate state details and is typically based on Photogate timing in graphical analysis rather than time-based data collection. Okay, so the labs we're going to look at today are projectile motion using a Photogate, and we'll add a time of flight pad to that as well. Pendulum periods. We'll look at Newton's second law from our advanced physics with Vernier lab book, where we're looking at using a Photogate on a cart and track system and looking at using that to determine the acceleration of the cart. The half-at wood setup there. We're going to explore the laser gate, and then we're going to looking at angular velocity of a wind turbine using angular motion tools in graphical analysis. I will note that these slides are available as part of the downloads that Angie has provided the link to. And there are two links on this last slide that give you the access to the user manual, link to the user manual, and then a link to one of our help articles on our website, setting up a Go Direct Photogate with graphical analysis. These are very useful tools, and you again have access to those through our website, but also if you download this this set of slides, you can access it and always have access to it that way. Okay, I'm going to go ahead and bring up graphical analysis at this point and start up a camera to look at our first setup. I have a tube that I'm using as a ramp, and we're doing a projectile motion lab. I'm just interested in capturing velocity data through this Photogate. I see that my camera's frozen up here. Just one moment. See if I can free it up. There we go. It's live again. So just getting the velocity through that Photogate of a ball bearing that is sent down the tube, and then students would use that velocity to determine where it's going to land. In other words, how far out. Based on the height of the table, they can calculate the length of time it's in the air and use that horizontal launch velocity to determine how far from the edge of the table it's going to land. So we'll just go through, again, this is just velocity data collection. So this is going to be our default. But first thing I'm going to do, I'll use this one to kind of show you what I'm doing. I'm just turning this Photogate on. and I'll get that indicator on the Photogate that it has Bluetooth is ready to pair. Even though that looks like a yellow LED, it's actually red if you have one in person. You're welcome to play along. So I'll turn on this Photogate and we'll go to sensor data collection in graphical analysis. Now, I have a bunch of equipment that is accessible to me, so I want to make sure I'm connecting to the right Photogate. On each Photogate, there is a barcode and a serial number. And that serial number, I typically use just the last 2 digits of the serial number to help me filter down to the appropriate one. So if I'm reading the serial number on the Photogate that I've set up here, it has U2 as the, N2 as the final 2 digits on the Photogate. And I can see now that's my Photogate, so I can connect to it. And I get confirmation by the LED for the Bluetooth is now flashing green instead of red. And I'm set up here. Object velocity is what I want. I'll just, again, expose you to all of the list of channels, but we're going to keep with object velocity for now. So I'll just click done. And we're going to get our information showing up here. Let's see. I want to bring this down ever so slightly. There we go. I'm just going to show this as a, as a meter. I really don't need to graph any data because I'm just capturing a data point, logging it, capturing another data point as I send the ball bearing through the tube a multiple times. And I do want to, I'm gonna show you another tool in graphical analysis that I find useful. This is presentation mode. I can make this larger so it's a little easier to read for you looking at your computer screens, and also for your students if they're at the back of the class. So again, that was clicking on the 3 dots and choosing presentation. Now, I'm not hitting the collect button. It's just going to give me an instantaneous readout when the ball bearing goes through the eye. So there we have 0.91 meters per second. I can do that a couple more times and come up with an average. Of course, it's going to vary a little bit depending on how I release the ball bearing, but I can come up with a pretty good average. You can also create, more sophisticated release mechanisms. At one point, I was trying to use a ruler through this slit to lift up and get a more reliable, reproducible release of the ball bearing. But again, we're getting pretty consistent 0.9 plus meters per second for our horizontal release velocity. And then with that information, we can calculate, first of all, based on the height of the table, the distance or the height of the table to calculate the amount of time the ball bearing will be in the air. And then with that, determine how far away from the edge of the table it will land. I want to add another feature to this lab, which is to use our time of flight pad. See if I can figure out how to get this in the picture here. So the time of flight pad is kind of like a Photogate in that it just registers when the ball bearing lands on it. And it does that through a cable connection. So there's a particular cable that will connect a time of flight pad to the Go Direct Photogate. And that's pretty much what it's called. It's called the Go Direct Time of Flight Pad cable. Amazing. So the cable has 2 different connectors on it. This one, it's kind of hard to see if I can figure out how to show that a little better. The tab is in the center there. The other cable has a tab on the side. And the tab that's on the side fits into the Go Direct Photogate. So I'm just going to plug it into that remote port, which is the same as the port here, that black port right there. And then the other end goes into the time of flight pad. Now, note that has a thickness, so you're going to have to adjust the height that you're determining that it's dropping. But then we can place that on the ground, and we can determine the time of flight as well as the velocity going through the gate. Because I'll show this to you a couple of times, but because I'm not using this collect button, I am free now to continue to change my setup. So I'm just going to go here back to sensor channels. And I'm going to add remote gate timing. And so what this is going to do is going to give me a timing of the from when the ball bearing breaks gate 1 until it hits the time of flight pad. And I'll just click done. Again, it takes me back to graphs. I'm going to just use meters instead. And that we should be set up now to be able to collect data, both the velocity and then the time that the ball bearing is in the air, to just confirm the calculations that they have made. I'll go ahead and go down there, and you see we capture the velocity and also the time in the air, so they can confirm that their calculations are correct. And I'll just do it one more time just to show us how that works. Again, a little different velocity that time, dropped a little bit differently, but the data should bear out the timing and the velocity calculations. Okay, so I'm going to take a second and kind of readjust my equipment here for a pendulum timing. It's a good time if there are any questions in the chat, perhaps Viral or Angie can let us know and we can try to answer them.
So it looks like we may have answered all of the questions so far, but feel free to put them in now and we'll get to them. Or just wait a moment and Tom will have the next setup ready. And there was a question about wanting to know more about the setup. And I did want to let everybody know that the experiment files will have directions on how to set up the experiment. And we also included a folder of photos of each of Tom's setups that he's doing today. So that will be a reference for you as well. And if you have any questions about the setup, we're happy to help. You can email us at physics@vernier.com.
So I have pretty much the setup here ready to go. You can see on this side of the Photogate, we can see the eye is blocked. So that indicator shows that we have the pendulum set up here. And I just have a string taped onto a bar on a ring stand. And that double string, that V string, is very useful in helping the pendulum, operate in a plane rather than kind of wandering all over like a Foucault pendulum or something like that. For this type of setup, we're just going to use one photo eye of our Photogate. And again, since I haven't yet collected data, I can simply come back to my sensor setup and I can select a new set up altogether. So I'm going to just have a single gate. I have to think about which gate it is. It actually doesn't matter too much, but I want to be consistent as far as I have gate 1 blocked, and let's go ahead and select gate 1. So when I go well, go ahead and go back to our graph settings, and it defaults. You'll notice the mode is Photogate Timing versus time-based data collection, and it defaults to linear motion, assuming that we're using a picket fence or something like that. Since it's just a simple sensor, it doesn't know exactly what's going on yet, so we have to kind of set it up. So there are a variety of Photogate timing options. There's speed through the gate. There's linear motion that's looking for some sort of a device like a picket fence or ultra pulley or something like that. There's angular motion. There's timer or period. That's where we're going to end up. And there's a projectile launcher because it's a Photogate device as well. But we're interested in the period of a pendulum. And so we click on timer or period and then click on period. Okay. Now the pendulum period is going to determine the period. It's not going to give us intermediate data necessarily. It is interested in when the gate is first blocked and then swings up and it comes back, blocks it again, and then swings up and then blocks it that third time. On that third blocking event, it's going to determine that period and report that period in our data table. And I'm just going to get this in motion, and I'll hit the collect button this time. And we can see our data streaming in here, and we get our actual period coming across as each time it goes through a cycle, it's going to calculate the period of the pendulum. Now, in this lab, like most pendulum investigations, you're going to have your students, change maybe the mass that's going through the pendulum, maybe how far back it's being pulled, and then, of course, needing to change the length of the pendulum so that they can go through that investigation and determine which factors affect the pendulum period and what that relationship might be. I'll just stop that so it doesn't cause us too much more confusion there. I have these are all just single data points. I could leave them as data points, or I can come down here to graph options. It's always easier on my eyes for some reason to look at a line of data versus data points, but data points certainly a valid option here. I can pull up the statistics to see that our mean value is for the period is 1.248 seconds. And there's some statistics there on minimum and maximum values. Excuse me, see if I can actually move that up and down. My mousing is not great right now, so. Okay, but there you get a minimum and a maximum value as well as the mean. If I do that, you can show that there. Good. So that's a pretty basic setup for the pendulum period. Again, you're only using one gate and going into setting it up through the Photogate timing mode and selecting a timer or period. Okay. All right. So in this case, we have actually changed our, we have collected data. So I'm going to start a new experiment. But before I do that, just going to disconnect that Photogate. I have a separate Photogate set up for our next experiment, which is our half Atwood machine. And let's just go ahead and, well, before we get started on data collection, let's talk a little bit about what we're looking at here. I'm just going to expand this picture a bit so we can see it a little bit more clearly. Okay, so this cart on a track, we have our Photogate here, just a hook on the end of a basic cart and an ultra pulley in the eyes of the Photogate there. On the end of the string, I have a tiny mass for our the driver, the pulling force in this experiment. And I want to go through how this actually connects to the track, just so that we're clear on that connection. So first thing I'm going to do is just remove the Photogate from the bracket there. And the cart and track system comes with this attachment bracket, just like a little L bracket, has this nut that fits into the groove that's on the bottom of the track. And it just snugs right in there. So just fit that in there, tie it against the track and tighten up that screw so that it's nice and secure there. And then I'll set this down here on the table so it doesn't get away from me. The ultra pulley connects to the Photogate here, and you can get that started. This part of the pulley, or excuse me, of the Photogate slides over that bracket that we just put there. So I can, before I do that, let me just turn this on. And well, this is instructive, so let me hang out here for just a moment. So you notice this photo eye is blocked right now. And if I rotate the wheel, it blocks and unblocks. The number 1 Photogate or photo eye does not get blocked by the ultra pulley in this scenario. So we're going to be using just gate 2 on the Photogate when we go to set up our sensor data. And this Photogate has a serial number that ends in U2. So I'll have to remember that when I get into the software to identify the right sensor. So again, we have the cart. And I'll attach the mass to the string. One of the other things you have to be aware of with this half Atwood setup is you want this string to be parallel to the track. So I need to adjust this a little bit. I can just loosen this screw and get that so it looks like it's pretty level, and then tighten it up again. Just kind of align everything, make sure things are true, as true as possible. Okay. And I'll just let it rest like that while we get the software set up. Okay. So I said U2 was the one. Again, I can use this filtering device. I could use Proximity Connect, but because I have a desktop computer, I'm not really sure which sensor is closest to my device there. So that should have, let's try that again, U2. There we go. So I'm going to click done, and then I'm going to click new experiment. Because I have collected data now, I need to start a new experiment in order to clear out that data and have a fresh start for my new experiment. Again, the default channel is object velocity. We're interested in gate state 2 instead of object velocity. So we're going to use gate state 2 in order to calculate the acceleration of the cart as we investigate Newton's second law on a cart and track system. We'll come here to Photogate Timing, and we're looking at, again, in Photogate Timing, since we chose gate state, it's going to choose Photogate Timing. And then it defaults to Vernier picket fence, which is not what we have going on here. We instead have an ultra pulley in the groove. So the ultra pulley in the groove just indicates that there's a string in the groove rather than rolling the ultra pulley across the surface. If you chose the other outside edge, you'll see that this number changes ever so slightly so that it's determining the basically the arc of the ultra pulley as it rolls across a table, as opposed to the arc of an ultra pulley when it's a string going across that slightly smaller radius. It knows that an ultra pulley has 10 flags, so we don't have to worry about that. You could just have this stop after it does a full revolution. I just want to manually stop data collection, so I'm going to click on that, and I'll click done. Now I'm ready to collect data. I can pull my cart back. Go ahead and pull it all the way back, even though you can't see it now. And I'm just going to hit the collect button and let it go, and then stop it. And then I'll stop data collection there as well. Now, obviously, I interfered with the data right in here a bit, but this portion of the data is pretty much just acceleration, constant acceleration data associated with that particular pulling force and mass. So in my tools, again, just my personal preference, I like to look at lines versus points. So I'm going to pull that up there. I can, I'll just click out of that. And then I'm going to take a look at a curve fit here. I can look at a quadratic curve fit, apply that, and I see that my A value in my quadratic, which is 1/2 of my acceleration, is about 0.15 meters per second squared, based on the ultra pulley. If I wanted to, I could also pull up another graph. So let me do that. 2 graphs. I don't need a data table. And on this graph, I'm going to look at velocity instead. And again, just because that's my preference, I'm going to change this to look at a line. And I can take a look at that curve fit as well. I'll just use it as a linear curve fit. And we can see our acceleration value for this. The change in velocity over time is about 0.3 meters per second squared, which is consistent with the value we got up there. So, yeah, that's the gist of that. Of course, in the lab, you would be, either changing the mass that's being pulled, or you're changing the pulling force and looking at that relationship between force, mass, and acceleration to get to the to an understanding of Newton's second law in this scenario. Okay, I'm going to change gears once again. I'm I can abandon that Photogate. So I'm just going to disconnect the Photogate there. And we're going to transition into looking at the laser gate and playing around with that a wee bit. So let me change camera views for a bit.
And there was a question that I answered, but I think that maybe others would be interested in this information. So Tom is using our graphical analysis app. So I'm going to put in the chat the link to the website, and then I'll also provide a code where you can try out the pro version for free. But that is the software that he is using today to collect the data.
So thanks, Angie. The laser gate basically just uses an ordinary pen laser. I happen to have just a red laser here. And we use this Photogate to demonstrate. So we're looking at shining that laser into this eye. And when that connection is made, when you're shining a laser in there, it's considered unblocked. And then if you have an object that's too big to fit through the arms of the Photogate, if you can separate this a considerable distance and still have it effectively be unblocked and blocked when, or excuse me, I did that backwards, didn't I? Unblocked and blocked when the object rolls through. So let me just turn my laser on so I can line it up here. Sometimes it's easier to move the laser, sometimes it's easier to move the Photogate, but you need to just get those lined up. And so this might be more interesting actually if I turn this whole system around. So I'll just go ahead and do that. Try not to blind myself in the process, but let's see if I can find that again. So there we are. I can move that a little bit and push that up a bit. So now you can see that Photogate or the laser is shining in the Photogate eye, and I can block that there. So I do need to turn on my Photogate again, and that's going to again allow me to play around with that. Get it set up there. Okay. Now the question is, which Photogate is that? That's number N2. So I'll just click on N2 there. And we're going to look at the laser gate, and it's just going to give us gate state. So kind of the simplest setup. I'm going to start a new experiment so I can get rid of that other data. And again, choose sensor data collection. And just make sure we have that selected. Oh, here we go. So it's defaulting to time-based data collection, but we need to kind of give it some more information. So it can tell us, gate state, it's blocked, unblocked. But if we want to calculate a velocity, a speed through the gate, then we need to provide it with some information about the dimensions of the object going through there. Now, this is a little tricky because here I have a ball that I know the diameter is about 7 centimeters, but I'm not completely confident that it's going right through the middle of the Photogate. So just know that this is an area you have to be careful about how you set it up and somehow determine what the actual blocked diameter of a ball is, or if you have a different shaped object, maybe you have a cart, more rectangular object, a little bit easier to definitively say, yeah, this is 12 centimeters long. I know that the true diameter of this is about 7 centimeters, so I'm just going to choose 7 here for demonstration purposes. And it's just going to collect a velocity each time I go through here. Again, I could instead use the meter, but it's just going to give me, I believe, blocked and unblocked information here. So let's go ahead and get set here, collect some data. Now, you'll also notice that it's going to depend a bit on the angle that my object is going through the Photogate. And I've obviously done something funky here because I'm not seeing any data. So let's make sure I connected to the right Photogate. That's my first step. Looks like I have gate state, laser gate state. Okay. That's good. Come back here, speed through the gate. Okay, let me.
You have, Tom, you have nothing plotted on your x-axis. That's part of your
Aha. Thank you, Vero. Didn't like that either. Let me start a new experiment just to kind of clear everything out. Okay, now it looks like we're set to go through speed through the gate. And let's use our known flag width of 0.07 meters. Call that good. Sorry, I'm floundering around here just a wee bit. I'm gonna get this straightened out here momentarily.
check your channel setup.
There we go. Because I started a new experiment. Still says gate state. Okay, that looks like it's set up for velocity and time. Not sure exactly what I was doing there, but at any rate, we're set up now. And let's go ahead and hit the collect button and collect some data there. So now we're getting our velocity plotted through there. And again, as I mentioned before, if I go through at, well, that's not a good example, but at a diagonal, that's going to be different than going through straight across because I've effectively increased the diameter of my object. So there are several things to take into consideration when you're using the laser gate. It is helpful for allowing you to use objects that are larger than would fit nicely through the Photogate, or where the object might actually collide with the Photogate as it's going through it. And there are some nice options if you have a large, like a mousetrap car, for example, and you want to know, what the time is that it goes over a certain distance. You can use the laser gate with a remote gate as well. Okay, I'll set that aside for now. I'm gonna just stop our data collection there. And the last thing I wanted to set up and show you was using angular velocity. And I'm going to use our Kidwind equipment on this setup. So let me bring in a mini Kidwind and figure out how to set this up so you can see it best. I actually need to just bend that up a little bit. Okay, now I'm just going to lift this up on the top of the, let's see. If I put that there, you should be able to see that the vane of the wind turbine is breaking the photo eye. Because I'm interested in the angular velocity, I only need to choose one gate to get that. And just to show you, I'm rather than having a fan blowing the turbine, I'm just driving this with a battery. So not exactly how you'd run it in class, but it does demonstrate the setup here. So I'm still connected to the sensor, but I need to choose different channels. I want to use either gate state 1 or gate state 2. I'll just choose gate state 1. I'm pretty sure I block both of them there. And I'll click done here. And then let's start a new experiment. Cancel. See if I can go here to. Okay, so we're not, we're not interested in linear motion, we're interested in angular motion. So I need to somehow get things cleared out here. We'll just start a new experiment again, see if that does the trick. I think part of my challenges with the laser gate was just the idea of having okay, so because I've been flipping back and forth, I think I just need to start and stop and restart graphical analysis. Of course, normally you would not be running through so many scenarios when you're using graphical analysis typically, but let's go ahead and make sure that we're using N2 is the right one. And for our sensor channels, we're going to choose gate state 1. Okay, here we are. Now, the type of motion we're interested in is angular motion rather than the default of picket fence. So we click on angular motion. This gives us a choice of the number of spokes. In this case, we have a wind turbine with 3 vanes on it, so 3 blades. I'm going to choose 3 for my value there. I can have this report out in units of radians or revolutions or degrees. Maybe revolutions are going to be the most meaningful, and I'll click done. Now I'm ready for data collection. I can start collecting data and then turn on my wind turbine, and we see a little short there in the action. Don't cross the wires. Let's So I'm going to just collect a new set of data. So we can see that gradual increase and then pretty much a constant velocity moving through there. I'll go ahead and stop it now. Get that view there. Can also look at my, look at my velocity. And we can see that we get, we have this ramp up in velocity, and then we have the ability to capture that average velocity of about 9.5 revolutions per second. Let me turn that off so it's not a distraction. Yeah. So, combining this revolution information along with energy production from KidWin can provide just another layer of investigation for students to consider, load, wind speed and load, and maximum energy production. That's pretty much what I had planned for today. As far as just some basic ways to connect the Go Direct sensor to collect specific data for different experiments using graphical analysis. I'll go ahead and pause and see if there's any last questions or comments from people. Appreciate you guys taking the time out of your day to be with us this morning. And again, this will be, this has been recorded and will be available on our website in the near future. Angie, any last words?
No, just an additional thank you for joining us. We appreciate you taking your time today. And if you have any follow-up questions, I'll provide the details to contact us in the follow-up email that will be sent in the next day or so. So thank you again for joining us. We appreciate it.